Okay, I think we'll start. Let people stream in. So we are very happy to have Narayan, who is going to tell us from the Chennai Mathematical Institute, who's going to tell us about aspects of extremal surfaces in ADS.
Okay, it's a pleasure to be here, and I thank Anindya as the organizer of this nice meeting. So I'm going to be talking about certain aspects of extremal surfaces in ADS-CFT and de-Sitter space. So here's an outline. I'll begin by talking about certain various non-relativistic investigations that have happened over the last few years on Lifshitz and hyperscaling violation. And I'll review certain gauge string constructions that I had and that have been developed since then, and I'll discuss entanglement entropy in them. This will suggest a Lightlike limit of entanglement, which I'll then discuss. I'll then talk about certain different work on DSCFT at uniform energy density and a de-Sitter bluewall, as we call it, and I'll close with some speculations on de-Sitter extremal surfaces. So this thing works, right? So over the years, we've seen many explorations and generalizations of ADS-CFT, example to non-relativistic systems, holographic condensed matter, as it's called, time-dependent systems, cosmology, and so on. Among other things, this approach gives a geometric handle on physical observables, and a striking example that we've been seeing over the last 2 days, in particular from Rob's lectures, is entanglement entropy. This is the entropy of reduced density matrix of a subsystem. So in this picture, for example, this light blue slice here is like a strip subsystem. This dark blue stuff is the environment. One constructs a reduced density matrix for the subsystem by tracing over the environment. And then the entropy of that is the entanglement entropy of the subsystem with respect to the environment. This is as such a difficult quantity to calculate in field theory. About 8 years back, Ryu and Takenagi gave a simple, powerful bulk prescription for this entanglement, as we've seen over the last few days. This essentially involves constructing a minimal surface like that. You look at all possible surfaces that bound the subsystem and dip inwards in the radial direction, and calculate and find that surface which has minimal area, which extremizes that area action, and the area of that minimal surface in Planck units is the entanglement entropy. This has survived many checks and it has been generalized, and there are many generalizations and so on. Operationally, what's happening is that one defines a spatial subsystem at the boundary. So this entire thing is on a constant time slice in the bulk d+1 dimensional geometry, and then the surface dips in the bulk and so on. Okay, and then one extremizes the area functional, and this is for minimal. These are minimal surfaces for static systems. In general, in time-dependent systems, these become extremal surfaces, as was generalized by Hubani, Rangamani, and Takenagi. A feature that comes out of here, mirroring what we expect in field theory, is for ground states, is that the leading scaling of entanglement is the d-dimensional area law. So this is a bulk d+1 dimensional system. The boundary is d-dimensional, is d space-time dimensions, and the leading scaling here, if epsilon is the ultraviolet cutoff, is the area of the interface. This interface in units of the cutoff. Okay, so this is all well-known stuff. In the last few years, we've been seeing generalizations of ADS-CFT with reduced symmetries. So a rather simple example, is this Lifshitz spacetime that was found by Kashulio Mulligan and Taylor, Marika Taylor. This exhibits these symmetries. There are time and space translations, spatial rotations over here, and a scaling of this kind, and an isotropic scaling between time and space. So if I scale spatial lengths by lambda, time scales by lambda to the z. The z is called the dynamical exponent. These are smaller than Schrodinger symmetries, the symmetries of the free Schrodinger equation. So for example, Galilean boosts are broken here. As a metric, if Z is 1, this is just ADS in the Poincare slicing. And as a solution, as a gravitational solution, it's a solution to 4-dimensional gravity with negative lambda and a massive gauge field. Okay? So it's a fairly simple solution. There are many more general gravity phases that have been found. So these are, for example, some of these are of this form. They're conformal to Lifshitz. They've been dubbed hyperscaling violation by, I think, Suvir Sachdev and others, probably primarily Sachdev. So the conformally Lifshitz, this piece inside here is just Lifshitz. This theta here is called the hyperscaling violation exponent, and the di here is the dimension of, is the boundary spatial dimension. Okay. So these are these. Yeah. They are, all the curvature invariants are finite and they're the same as an ADS. Or no, sorry, they're not the same, they're finite, but there are tidal forces that diverge in the deep interior. So, you know, at this level, this is just a gravitational solution, but you'll very soon see when I talk about the string realizations, some of these things. But in general, so, you know, this is something that already was observed by Cauchy-Leuel and Mulligan, that there are these kinds of infrared singularities, tidal forces will diverge in the deep interior. And in that sense, they are a little reminiscent of plane waves, in the sense that curvature invariants are finite, but tidal forces diverge. And so there is a physical singularity in that sense. In this context, probably what it means is that if one thinks of these Lifshitz symmetries as exact symmetries, there also are exact symmetries of the dual field theory. We expect that there are more infrared modes for a theory which has a dispersion relation which is like that. So, you know, you might expect that there are more infrared singularities in just field theory, but this is still not completely understood. I mean, it's not. I mean, there's still stuff that one, yeah. So that's the best. That seems to be still the state of the art. So coming back. This is all zero temperature. I won't be really talking about the singularities at all actually much. I mean, I'm just sort of mentioning it because they are a part of the story, and I think the reason one expects this also, if you have exact Lifshitz symmetries, is this. As gravitational solutions, perhaps you expect instabilities because of these singularities, reflecting these singularities, which perhaps means that these theories have certain instabilities of some sort. That may well be. And so there have been investigations of that sort also in some ways. I'm not sure what the conclusion is finally. So in general, one might think of all of these kinds of things as intermediate phases which are there, which survive in some intermediate regime, and then they might, and the infrared phase, the true infrared phase, the true ground state might be something else, and so on. That could be. So so anyway, so coming back here, so these more general gravity phases are hyperscaling violating phases. They're conformal to Lifshitz. They rise in effective Einstein-Maxwell dilaton theories. And there's also a long history of this here. The actual space dimension of these theories is, the actual boundary space dimension is di. But if you look at the thermodynamics, for example, by constructing black holes in this, the thermodynamics reflects a space dimension, an effective space dimension, which is like di minus theta. And that's where this name hyperscaling violation sort of comes from. This doesn't look like, this looks like the theory has thermodynamics, which is sort of like a fractal space dimension in some ways. So sort of ruining hyperscaling in the conventional critical phenomena sense. If one looks at the entanglement entropy behavior, in this family, theta is di minus 1. One finds that the entanglement entropy grows logarithmically with the system size. And in fact, this was one of the motivations for various people, in particular these guys, Ogaba, Takenagi, Ogajin, and who would say Sachdev, Swingle. Bulk. I'll tell you very soon. But I mean, this is just standard Ryu and Takenagi in this context. Huh? Yeah. Yeah, actually, what? Hang on a second. No, by proof you mean what? See, there's no So the logic here has been, no. What's the question? Sorry.
Derivation of this. I think he's
Derivation of Ryuan-Takiragi. No. I'm sort of at this level. I'm not going to look at Lefkowitz-Maldacena or any of these other things. It's an interesting question to ask whether that can be done in this sort of thing. I think it's still open very much. The logic here is that one believes that this works in many cases, and one says, look, if I just apply these things to these kinds of more exotic theories, which are of great interest for various other reasons, then I find this as a diagnostic, and one can perhaps use this as a diagnostic to characterize phases. Okay, so as long as this relation holds. Yeah, as long as this relation holds, this is. But as far as these metrics are concerned, as far as these gravity duals are concerned, these theta and di are independent parameters. You could just do whatever. And in fact, you'll see very soon. Well, you'll see. Just hold on for a slide or something. Probably it will. In some sense, it's sort of trivially it might hold because this z is just sort of going along for the ride in some ways. But you know, it would be nice to actually see if that actually is true or not, right? I mean, yeah. So I don't think it's been done, and it might just be that there are subtleties that one. So in fact, part of the motivation for constructing these things were sorry. With the U1 symmetry and so on. So it probably should hold.
there's some extra matter that they need to add to support it. Once that is that goes through the usual checks.
Yeah, so it might well be true. In fact, it probably is in fact true. So so one of the motivations, in fact, that these guys had to construct these kinds of things, in fact, was reverse engineering these metrics of this kind as perhaps gravity duals of Fermi surfaces. Regardless of this, these are interesting solutions in their own right, and so various aspects of these kinds of hyperscaling violating spacetimes holography have been studied in this paper by these guys. And something that you see is that in this entire window, di minus 1 less than theta less than di, the entanglement entropy shows area law violations. Okay, here you get a logarithmic violation, and in this window you get something in between, something perhaps stronger. Okay, so so as gravity solutions, these are interesting and they exhibit certain interesting properties, interesting thermodynamics, entanglement, and so on. And one might ask, well, are there string constructions where this sort of thing can be seen explicitly and perhaps shows something for the field theory, perhaps vindicates some of this, perhaps tightens this parameter range, and so on. And so there are various string constructions. The various string constructions in part that I have been involved in and various generalizations thereof involve spacetimes of this kind, and where G++ is positive. So this part, if G++ is 0, this is just ADS across some sphere, things that arise in various near horizon geometries of various D-branes and M-theory branes. One starts with a spacetime like this and does a dimensional reduction along, thinks of x plus as a compact dimension and does a dimensional reduction. And in this process, in the lower dimensional theory, the time ends up being x minus. Okay, so an example of this sort is this. This is some work nearly 4.5 years old by Kaushik Balsamanian and me, and a little later by Donaldson Gauntlet and various other people who generalized this. So this gives rise to z equal to 2 Lifshitz. These are non-normalizable deformations, non-normalizable null deformations of ADS cross X. And in this case, the G++ as a simple example, so G++ in general is sourced by some light-like matter. So in this case, a simple example is I take a light-like axion, the G++ then is like that, and this gives a z equal to 2 Lifshitz spacetime like that. Okay. So certain hyperscaling violating spacetimes can also be realized along similar lines in spirit, but in detail quite different. These I call ADS D+1 ADS plane waves. They're essentially structurally similar to this, except that this G++ is a normalizable piece. So in fact, if you look at this, you get spacetimes like that. These are in fact in the same family that I was talking about earlier, these hyperscaling violating spacetimes. But these exponents now are fixed. They're not, they're coming from things that I start with something very specific in the upstairs description, which I can control, which I understand. And that gives me a certain family of hyperscaling violating spacetimes with theta like that and the Lifshitz exponent like that and so on. So these are actually, turns out, to be normalizable G++ modes. And so in fact, these are the simple interpretation of just certain fairly simple dual CFT excited states with an energy momentum density T++ turned on. If you do this correctly, this T++ is basically just Q, this parameter here. Okay. So these can also be thought of actually as large boost, low temperature limits of boosted black branes, it turns out. Okay. So, so in particular, sorry, somebody had a question. These in fact actually are, both of these actually are formally like Schrodinger systems, but with a minus, with analytically continued. So this is like a z equal to 0 Schrodinger, and this is like a z equal to minus something. I mean, you know. There's no x plus is a circle. So this is positive. Therefore, you can compactify in the bulk. So the x plus direction is compactified to construct the low dimensional theory. But once I have these upstairs constructions, I could just ask what they mean, because here I can actually identify what the field theory is and so on. So and it better be that if this is a faithful construction, that various properties, thermodynamics, entanglement, and so on, that I see downstairs do in fact mean something upstairs. So that's what, and that turns out to be true. Okay. So so here are these hyperscaling violating like spacetimes. They are fairly simple excited states in the CFT. In particular, for the ADS5 plane wave, what we find is that this D here is 4. The boundary space dimension in the lower dimensional theory is 2. Theta is 1, and Z is 3. And so this in fact gives this logarithmic behavior. So the point of view that I'm going to take now is that I started off with these lower dimensional theories. One could just study entanglement in these low dimensional theories and one knows that there is some interesting behavior in these kinds of windows. Here are some of these concrete gauge string realizations. One therefore expects that similar behavior persists in these kinds of things upstairs, perhaps in a certain regime, and it's useful to therefore ask, well, what does this mean for the Yang-Mills? Okay. The entanglement in particular in these theories, focusing just for the ADS plane waves for now, matches. So the entanglement upstairs matches the entanglement in the lower dimensional hyperscaling violating theory. If the upstairs entangling surface lies on this x minus equal to constant surface, which is a t equal to constant surface below. So what I'm doing is that I started off. So I have this low dimensional theory where I have time, and as per the operational procedure that you and Takenagi do, you would take a constant time slice there, construct, carry out the entanglement entropy procedure in the bulk. Lifting this essentially means that this entangling surface upstairs lies on an x minus equal to constant surface. This is really this x minus is like cone time. Okay, so it's a little more actually, to be precise, but I'll get to that soon. Now this might look a little mysterious, and I still don't understand it very well, but I'll tell you a little more in some time. Meantime, one can ask, let's just think of these things as excited states in the CFT, and ask, let's construct space-like strip subsystems, because these are essentially energy flux in a certain direction, like here. So a strip is a natural thing to consider upstairs. It's along the lines of the symmetries. And I ask, what happens if I just consider space-like strip subsystems and study their entanglement? Okay. So these are non-static spacetimes, and this is some work that I did with Tadashi and Sandeep, Tadashi Takenagi and Sandeep Trivedi some time back. These are non-static spacetimes, and so one expects to use the covariant formulation of entanglement that these guys had. They're not terribly bad to do because they're just sort of non-static. They're not really badly time dependent and so on. So calculation is a little more involved, but it's okay. So So here's the kind of thing that happens. The strip, the flux direction is going up like that in this picture. You could consider strips that are along the flux. These are sort of natural from the point of view of the downstairs description. And let's say I take one of the width directions to be one of these xi's. The strip is along the flux. The leading divergence that you get in this case is always the area law. Okay, so this is the usual area law that we see. The leading divergence is proportional to the area of the interface in units of the cutoff, epsilon. There's a subleading finite cutoff independent part, which is like that, which can be estimated to be that. This just follows from the bulk entanglement area integral, and you can see that there's a finite cutoff independent piece that one can be that you can extract out.
And operationally, what you do is you set x plus to be a function of little r, and as well as.
So I'll tell you in a little more detail what I'm doing, but just to give you, so what we are doing is, in this case, what we are doing is thinking of x plus as something that goes along for the ride, because it's really something that I eventually think of as compactifying here. Except I can think of that in the same spirit upstairs. So x plus really doesn't do very much. It's again a non-compact direction, but it's along the strip. Okay. So the x plus direction really is subsumed in here in the longitudinal part of the strip, basically.
So where exactly are you using this covariant?
So the whole formulation of this really only is well defined in this covariant formulation. In this covariant formulation.
Operationally, then you just put x1
Operationally, yeah.
X to be a function of r, and then
X is so if this width direction is say x, for example, one of the xi's, then the x is a function of r, and that minimal surface is so it's just something like this. It dips like that. So yeah, so it's very similar to this. One of the directions along this thing is the x plus direction. In the other case, it's much more involved. So here, one could also consider a strip. So anyway, let me just finish the story and then I'll tell you what happens there. So you can extract a finite cutoff independent piece here, which looks like that in D boundary space-time dimensions, D-dimensional CFT. In particular, for D equal to 4, one gets something like that, and this looks basically like the Fermi surface answer if you identify q to the 1/4 with the Fermi momentum. Okay, then it's exactly like the Fermi surface answer. These are so independent of that point of view. These are just certain kinds of excited states. So I can think of these as excited states and ask what two other kinds of excited states. For the ground state, you get a finite part which looks like that. It scales like the area of the interface in units of the width. So this is greater than that. That I expect, because if I'm pumping in energy density into the system, I expect that, or at least I might think that the finite cutoff independent piece is in some sense a measure of the number of degrees of freedom, and that's true. It's also less than the thermal entropy. So these are so that's also not perhaps surprising, because these are a certain limit of the thermal state. They only carry a certain fraction in some ways, and so you might again think that they should be subthermal. Their entanglement also should be subthermal, and that's also true. Okay. So there's more to this here. There are more general non-conformal generalizations of these, and you'll see the same sort of thing if I get to that. For the strip perpendicular to the flux, so the flux direction is like that, and the strip is, let's say, like this. It turns out that there's a phase transition. Here, the covariant formulation really is something that one has to face up to in a more serious way. You really have to think of these x plus and x minus as dependent on r, and there's some surface that's a bit of a complicated thing. But and so that also shows that there is a phase transition. In practice, what that means is that there's no connected surface if one insists on space-like subsystems. Okay. Well, here's a story. So you can see that for these kinds of plane wave excited states, one gets a finite part. This is the same thing that I flashed earlier. You get this leading behavior for the D3 brane, which is a logarithmic behavior. You get a power law growth for the M2 brane, which is actually bigger than log. There are more general non-conformal brane generalizations of this sort, which can be studied like this, where there's again a G++ piece, and that's the only piece that's different from the Itzhaki, Sonnenschein, Mardisana, Sonnenschein, Yankelowitz story of non-conformal branes. These essentially are strongly coupled Yang-Mills theories with a constant energy flux. And if one studies entanglement, you again see a similar thing. You can again estimate the finite part. The ground state story is already a little more intricate there because there's a coupling which is dimension full, and so one sees that there are coefficients that appear here which are actually some non-trivial functions of the coupling of this dimensionless of this scale dependent number of degrees of freedom. So it's not just n squared, it's some more complicated thing. Along the same lines, one can also do the plane wave calculation for these plane wave excited states, and one gets a finite part which looks like that. The bottom line is that in cases like this, where one can compare, where one has a full RG flow, for example, like the D2 M2 brane system, one can see that the finite part for the D2 brane is in fact something nice. It lies in between the free three-dimensional superangles in the ultraviolet description and the M2 brane in the infrared. So these satisfy actually various consistency checks, and it sort of suggests that this finite part in some ways perhaps is to be taken seriously, and it actually means it actually is like a measure of entanglement in some ways, and the number of degrees of freedom in some sense. Now, yeah. So one can also study mutual information for these kinds of things holographically. Mutual information essentially is this linear combination that Rob was in fact talking about earlier. There are no cutoff independent divergences, they just cancel. And holographically what it means is that one, for example, in the context that I'm talking about, one considers two strip subsystems, one considers, one finds the non-trivial part of this calculation is the extremal surface for the A union B. And so when the two subsystems are far apart, you expect that these two little bumps, these independent surfaces are lower area, because it costs a lot of energy to, it costs a lot of area to construct this. But when they are nearby, there is a connected surface, which in fact turns out to have lower area, and this has been checked for various ground states and so on and so forth. And so, Matt Hedrick pointed out some time back that the Ruyen-Takanagi prescription automatically suggests that there is a disentangling transition for mutual information in the sense that when the strips become further and further apart, you see that there is a sharp transition of this kind for mutual information. This is non-zero when the strips are nearby, and it vanishes when they're far apart. Okay, so we studied the same sort of there's a similar structure for thermal states, it turns out, and we had studied mutual information for these ADS plane wave excited states. And so there's some story here. The bottom line seems to be that the mutual information disentangling transition occurs faster in the sense that the critical separation is smaller. Okay, the strips disentangle faster, basically. That sort of suggests that the energy density disorders the system, and whether this is an indication of something more, whether this can be quantified and systematized more, is something that might be interesting to do. Okay. So what have we done so far? We've studied these ADS plane wave type upstairs string constructions for some of these low dimensional theories, and I've just outlined a collection of properties for you of the entanglement if I just look at the upstairs theory itself for space-like subsystems. Now we go back and recollect that the entanglement here matches the entanglement in the low dimensional theory only if the so this suggests that the entangling surface in the upstairs theory lies on this x minus is a constant surface. Okay. So to do this a little more in detail and to isolate perhaps a Lightlike limit here, let's just go back to setting this up in a little more detail. So I construct a subsystem like that, a strip subsystem. So here these x plus and x minus are traded off for time and a third dimension x3, for example. In the usual space-like subsystem, what I would do is I would just take alpha and beta to be 1. That then means that the subsystem lies on a constant time slice. Okay. Here I want to do something more. I want to take a general subsystem which is oriented possibly differently. And if one sets up this calculation, what you find is that this is the sort of thing that one finds, and this is already something that we had studied at some level in the paper with Tadashi and Sandeep. Again, in the space-like case, if these parameters are just like that, if the strip is purely space-like, you get an area law which is the leading divergence. Okay, that can be seen from just this piece here. This leading divergence here is just this. If R is sufficiently small, when you're sufficiently close to the boundary, all these terms go away, and you end up with just a constant that's left over here, and that leaves this leading area law divergence. Okay. So that's where this is coming from. That's where the leading divergence is coming from. Now, if I look at the other limit, which is the limit of interest here, the limit of interest here is a null time slice, an x minus time slice. For here, I would just set beta equal to 0. This would then give me x minus equal to 0 as a time slice, and this is just some parameter now. This this entanglement integral looks like that now. This holographic entanglement integral looks like this. Okay. So now notice that even if we are very close to the boundary, there are still factors of R and so on that survive here, and this actually changes the leading divergence behavior. Okay. So I'm going to dwell on this a little more, but let's just see. So I want to just notice the following statement, that one can perhaps define this Lightlike limit as a highly boosted limit of the entanglement entropy for a space-like subsystem. So I would just start with a space-like subsystem like that, and then I boost in this fashion. This then transforms, this then reorients the strip in a highly boosted direction. The entanglement entropy turns out to not be boost invariant, and so you actually get something non-trivial. And so what you end up with is something like that. Now, in a certain regime where which quantitatively is like this, this essentially is approximately the same as this entanglement on this null time slice. Okay. So so let me just tell you a little bit about what this might mean. So what you see here is that if one does this if one takes this Lightlike limit and sets this up in this regime, the subsystem is stretched on this x plus plane. So this is a subsystem like that. The leading divergence now is actually milder. Okay, the leading divergence in fact is not the area law in the usual area law. The leading divergence is in fact milder, it turns out. Okay, there's another thing that one can see from here, which is that if one looks at the ground state, these are all excited states that we were talking about, or CFT deformations. If one looks at the ground state itself, this Lightlike entanglement, in fact, on these null slices, in fact, just vanishes. Okay, this is something that's been noticed that we had noticed earlier also, but this is a general in the context of the ADS5 plane wave. But this is a general story, it turns out. Okay, and it's also most recently made an appearance in some of these investigations of Busso, Cassini, Maldacena, and Fisher in the context of investigating the Busso bound and so on. But here, this makes an appearance in this context. So, so just to recap what we've done, we saw that these hyperscaling violating theories exhibit some novel entanglement scaling of sorts. We had these string constructions, and so we asked, does this really mean something for the field theory? And so here is a hint of what it might mean. Okay, so if one sets up this this Lightlike limit of this in this fashion, what you see, for example, in the ADS plane wave in this regime is that the entanglement has an expression like that, and this integral essentially is actually solvable. It's just like an ADS integral, it turns out, and you can actually just do this explicitly without any approximations. And so, among other things, the leading divergence is in fact milder. The finite part is the same as what we saw earlier. The leading divergence is milder, and this whole structure is sort of reminiscent of ultralocality in light cone field theory that Aaron Wall has been had studied not long back. So this is a statement in field theory that in the ground state, endpoint functions of field operators which are at distinct locations on the null generators, they're all distinct. So imagine inserting field operators at distinct generators of the null surface. These endpoint functions all vanish. This is actually a statement in the interacting theory, but here I'm just hinting at this in the weak coupling in the free field limit essentially. So if these correlation functions vanish, it might suggest that the entanglement also vanishes in the free field limit. So for the excited states, one can in fact show that these free field correlators are in fact non-vanishing. You can just take a simple free field, free light cone field theory quantization, for example, and construct excited states which have non-vanishing light cone momentum, and you can actually see that free field correlators are in fact non-vanishing, and so that again suggests that that's again sort of in sync with this. It's at least consistent with this. It's not a statement that this implies that or what. This is a bulk calculation, and these are just free field statements that I'm making here. It might be interesting to understand if one can systematize this to study entanglement in weak coupling in this context. Okay. So I'm going to move on to slightly different things. So I'll pause if there are any further questions on this. These things are free field, yeah, free light cone field, yeah, just scalar fields and so on, for example. No, these are actually all relativistic, and in fact, all these constructions essentially have transformed these to just simply certain excited states in the field theory. So I'm talking about relativistic Yang-Mills, for example, with certain excited states, and there are certain properties of those excited states which this is pointing to. That's right. That's right. Yeah. So here, all I'm doing is I'm not even, I'm looking at, fairly simple excited states as just hints of what might be happening here. You just start with excited turning on oscillators which have non-vanishing light cone momentum and seeing what they do, and then ask if free field correlators are non-vanishing. If they again vanished, that's again not inconsistent, but because you might just imagine that this is all weak coupling and that's strong coupling. But the system is all supersymmetric and so on, so maybe that's not expected. So, yeah. Any other questions? Okay. So one can do a similar study in the Lifshitz theory also, and I'm not going to go into that. I'm going to move on to a slightly different context, which is de Sitter space. So de Sitter space is fascinating for various reasons. Among other things, holographically, there have been generalizations or conjectural generalizations of holography for de Sitter space, dubbed DSCFT. This essentially is a statement that fluctuations about de Sitter are encoded through a dual Euclidean non-unitary CFT on example the boundary at future time like infinity. So this is de Sitter and Poincare slicing, and the Penrose diagram looks something like that, and I'm talking about this boundary there. So this is still very much mysterious, but it's perhaps interesting to explore. So in his famous paper on primordial non-Gaussianities, Maldacena in 2002, among other things, also pointed out that various bulk calculations can be in de Sitter can be reorganized as an analytic continuation from Euclidean ADS, ADS4, and they organize themselves into, in some sense, the rules of DSCFT, so to speak. Operationally, technically, the Hartle-Hawking wave function of the universe is to be identified with the partition function of the CFT. Bulk ADS regularity conditions in the deep interior map over into Bunch-Davies or Hartle-Hawking type initial conditions in de Sitter at early times. Okay, and this is something that you can see using this analytic continuation, for example. There's also something that you can see independently, but under this analytic continuation, these regularity conditions in ADS map over to this. Okay. In the semi-classical limit, this partition function is the wave function of the universe, which can be approximated as an exponential of I times the action, the classical action. Okay. Now this wave function is not, the wave function of the universe is not a pure phase, and complex saddle points in general contribute to observables. Okay. So, so something that we had explored last year in a paper with Shumit Das and his student Deep is a study of DSCFT at uniform energy density. Okay. So, so here's a class of asymptotically de Sitter spacetimes. These are in general, this alpha here is a complex phase. There are subleading normalizable pieces turned on. Tau equal to 0 is the boundary. This tau naught here is some real parameter of dimension length inverse. Okay. There's an analog of regularity in the interior that one can come up with in this context. So if one thinks of these things as possibly saddle points in a path integral, one would like these to have certain regularity conditions. So something that we came up with as the analog of regularity in the interior for an asymptotically ADS solution is the following. So we rotate the time direction and demand that the resulting spacetime, which is thought of as a saddle point, in the interior approaches a flat Euclidean space in the LW plane, where L is this Wick rotated time, and there is no conical singularity. Okay. So this is very similar to the kind of thing that one would do for a black hole, for example. In this case, what you find is that the W coordinate becomes angular with a fixed periodicity. This L then becomes a radial coordinate, which is the Wick rotated time, and this phase then gets fixed. Okay. So this phase is in general a complex phase, it turns out, and so this in general is a complex metric that solves de Sitter gravity. So it's an exact solution, and this entire procedure turns out to be equivalent to the analytic continuation from a Euclidean ADS black brane. Okay, so that's this. No, so R naught is held fixed. We don't analytically continue the parameters. So we continue the variables, we continue time and the ADS scale, but not the parameters. And it's important that in this DSCFT discussion that the parameters are not continued.
But then you get a factor I to the power D.
That's what this is. Yeah. So there's a general phase here, and you ask what this phase should be if this satisfies the singularity in the interior criterion, and what you get then is this. That turns out to be the same or equivalent to continuing from the ADS black brane. Okay. Now there are normalizable metric modes that are turned on here, as you can see, and so one expects that there's perhaps an energy momentum tensor expectation value that's turned on. For a three-dimensional CFT, this would be a natural definition for the energy momentum tensor. It's just a variation of the partition function with a boundary metric. That's equated by DSCFT to a wave functional derivative. That wave functional derivative in the semi-classical approximation has an I coming from here, for example. That I filters through here, and the rest is the variation of the action itself. One can do this calculation as an ADS, defining boundary counter terms and so on, but this I still persists. Okay. So in particular, what this means is that the energy momentum tensor here is real only if this quantity is pure imaginary. Okay. So in particular for DS4 CFT3, what you find is that alpha, this parameter here, turns out to be minus I. DS4 is D is 3. So alpha turns out to be minus I. The energy momentum expectation value turns out to be real. This metric is actually a complex metric now. Okay. I mean, this is just a statement that if the metric is complex, then Tij is real. If not, Tij is imaginary. So you'll actually see later what something else where you get something else. But it would seem that from a three-dimensional CFT point of view, you might want Tij to be real. So therefore, the metric then turns out to be complex. Okay. So in particular in DS4 CFT3, which is perhaps the best understood DS CFT, a real expectation value, real uniform energy momentum density, turns out to give a complex metric. Now one could have asked something else. One could have said, suppose I didn't take that to be the case. I started off with a metric like that, but I then continued the parameter also, so that I get a metric which is like that now. Okay. This now is a real metric. It has a Penrose diagram which looks like that. And that Penrose diagram essentially looks like the ADS Schwarzschild, but rotated by 90 degrees. Okay. So what you get, to just remind you, for the ADS Schwarzschild is something like that. Okay. And what you get there is that. So this thing is, so now these you can define crucial coordinates, so you can do standard GR now with this. And you can see that there are in fact two asymptotic de Sitter universes. There are time-like singularities here, and there are these horizon-like lines are in fact Cauchy horizons, it turns out. So in fact this entire picture, this Penrose diagram is very reminiscent of the interior of the Rice-Nordstrom black hole. And so on. So Rice-Nordstrom black hole in the maximal extension has a Penrose diagram like that, and this part here is the thing that, has been abstracted away to that Penrose diagram there. Okay. Now that's actually not surprising, it turns out, because this entire metric, if you look near tau naught, in fact resembles the metric that you get if you look near the inner horizon of the Rice-Nordstrom black hole, it turns out, or the wormhole in this context. Okay. You could ask what trajectories look like in this story. So there are various kinds of trajectories. You could imagine static observers simply just go through this bifurcation point, this bifurcation region, and they go from the past universe to the future one, or at least they appear to go that way. So these are these P1 observers that I'm calling here, these lines here. There are also observers that you might consider to be infalling observers which go like that, which go through. But it turns out that the singularity, just like in the Rice-Nordstrom case, is actually repulsive. So these observers that have finite momentum like that go through, but they get repelled and they in fact go back. They never actually hit the singularity as long as you're talking about time-like observers. One could study null rays, and those null rays in fact do hit the singularity and so on. So in fact the reason these things are called, the reason these things are Cauchy horizons, if you're not familiar with that, is that there is stuff here in these regions which can never be obtained by time development of any Cauchy data on this past time-like infinity slice. Okay. So these things are Cauchy horizons. They are boundaries they are boundaries for the Cauchy data here. Okay. Now you notice that there are these incoming light rays from infinity which are actually crowding here. So in fact these things actually mean something, it turns out. They actually mean that the late time infalling observer here in fact sees these early light rays blue shifted. Okay. So you can actually do a calculation and see that there are calculate the redshift or the blue shift, whichever you look at it, between early time infalling observers and late time infalling observers, and you can actually see that the proper time lengths between these guys is actually highly blue shifted. The late time guys see as it's called an entire history in a flash sort of a thing, just like in this case. So there is an infinite blue shift due to this Cauchy horizon, which signals an instability of sorts. If one does the standard DSCFT calculation like that, in this case, since this is now real, that piece in this context, what you find is that the energy momentum tensor is imaginary. So perhaps one might think that this blue shift instability is correlated with that instability in Tij, if this entire interpretation and the interpretation of Tij in this fashion is correct, and the interpretation of DSCFT in this light is correct. Okay, so any questions on that? Okay, so I'm now going to close with some speculations on de Sitter extremal surfaces. You might ask, what do you get if you if you ask if there's anything like entanglement entropy in DSCFT. Now maybe that's question one. Another question is you could just ask what happens if you study bulk extremal surfaces along the lines of Ryu and Takenagi, but in de Sitter. Okay. So to begin with, let's just do this operational calculation. Let's do the bulk extremal surfaces calculation. So a generalization here would start with a subregion at future time like infinity, but on a constant Euclidean time slice, construct the bulk area functional and ask about its extremization. So this you can actually do, this is straightforward to do. But now interestingly,
That's the question.
That's part of the question. I'm not sure that question as phrased makes physical sense or whether it.
That sounds like a good question. No? There's a wave function universe and you can ask.
I mean, I know. It looks like it should be a good question.
Okay.
I'm not sure if that's what this will capture basically. That's what I mean.
And now you want to see if that's given by something like extremal surfaces that
something like that. Yeah. So we'll find actually a bunch of answers and then we'll see what.
But now these are surfaces that are time-like.
They are not. Yeah, they are. Well, you'll see what they are. You'll see what they are very soon. Just in the next slide actually. So they are. So you can actually set up this calculation like that on a constant Euclidean time slice. The most important feature here is that there's this minus sign. A constant Euclidean time slice still has this time, the bulk time direction, which in fact is where this thing will dip in. So that minus sign actually means a lot, it turns out. So there's a conserved quantity that comes out in the extremization, which then translates to this quantity, to the surface being characterized like that. Okay, where B now is some constant. So the important sign difference here from ADS means that there is no real turning point. Okay, these x of tau surfaces are actually hyperboloid. So one could imagine artificially constructing an extremal surface by joining two half extremal surfaces like that. This again assumes that there is some sort of axis of symmetry. So I'm going to again focus on a strip-like subsystem, which is all I'm doing here. If I construct such two half extremal surfaces, you can see that since they never turn around, these surfaces will keep going down that way. You can formally you can see what the area looks like, the area integral for these surfaces, and it looks like that. Okay, this B parameter continues to appear here. These are a whole family of such extremal surfaces parameterized by B, and you can see that this area dips down if B increases, and so in fact as B increases, the shape itself saturates like that, and this in fact is becoming like that. This dotted line is in fact the ultraviolet cutoff surface, the tau equal to epsilon surface. And you might imagine therefore that if this quantity is B, this constant B is much bigger than the corresponding ultraviolet cutoff, the corresponding time cutoff that one imposes here on the future time slice. This surface is actually saturated, and this in fact is just a null surface completely. Okay, so the resulting surface that you get at the end of the day is this past light cone wedge of the subregion. Okay, this x of tau is a null surface, and it's got vanishing area, and so these are sort of analogs of this causal holographic information and the bulk causal wedges that Yubani and Rangamani have talked about. If this is all, this may be true, but it may be boring. From the point of view of DSCFT, one might ask if there are complex saddle points, complex extremal surfaces, and in fact there are. So it's going to look a little crowded, but let me just walk you through this. So recall that if I talked about from this conserved quantity in the extremization, I get this, and this entire procedure assumed that B squared, that we are talking about real quantities here, B squared therefore was positive, therefore there's no turning point of this thing. Okay. But if B squared is negative, one has a turning point, and this procedure then looks very much like the Ryu and Takenagi procedure itself in ADS. You get a complex surface instead that looks like that. The area integral then looks like this, where now I think I'm going to just be careful relabeling the ultraviolet cutoff on tau and the turning point tau star. Investigations in DSCFT suggest that this ultraviolet cutoff the tau ultraviolet should really be I epsilon. If you do all this, what you end up with is something like that. And you end up with a real quantity like this, okay, defined like that, here I've stuck in a minus I related to this. This quantity, as I calculated earlier, is in fact pure imaginary here. Okay. This quantity at the end of the day. So anyway, let me just zip through. So in fact, what you actually get, this might seem ad hoc. You might just say we've stuck in a minus I here to get something real. But in fact, what actually turns out to be the case is that this whole thing is in fact just the analytic continuation from what you get from the analytic continuation from the ADS Ryuan-Takenagi extremalization. Okay. So if one just started off from the ADS Ryuan-Takenagi area functionals and the extremalization solutions, what you get is you get a whole bunch of phases. These things are actually I squared, so you get various powers of I and so on. And this whole thing filters through like that. You always get real surfaces like that. So for example, if D is even, this conspires to give a plus sign, which is the same as the real surface that we saw. But in DS4-CFT3, for example, you get complex surfaces, and in general, actually, you get complex surfaces. The resulting area integral is also in general complex valued, it turns out, after analytic continuation. But in DS4-CFT3, the various I's just conspire in the right way to give something real, it turns out. Okay. Now, one can also show that in this DS4 black-brane that I was studying earlier, which looks like DSCFT at uniform density, there's a finite path that one can extract out from here, which in fact resembles an extensive thermal entropy. So answer 1 was those real extremal surfaces. Answer 2 are these complex extremal surfaces. And so as far as the physical interpretation is concerned, from the point of view of the wave function of the universe and so on, I'm not sure.
So this wave function of the universe is the partition function ADS. So what you need to do to compute the entanglement entropy is do some integral of the partition function. I mean, you've already been given the wave function of the universe. So you do the integral by identifying the partition function on, in different parts outside some region and do that partial trace. So that gives you an answer, I guess. And it's not clear why that should be anything like a minimal area surface, but you can presumably try and ask the question of what that is by starting with this identification.
Yeah, I'm not sure if this is what that is.
But in some sense, you're guaranteed you take a surface and you do an analytic continuation, you'll go back to the ADS problem with some quirks. For example, the ADS
That's right.
problem might be an S3, but you can never be an S3 here because your surface is always non-compact at late times.
You could study strips there and strips here. So so that's what I'm doing here,
so
and that.
Always go back to the infinite volume ADS problem, right? So
yeah.
Right, but the thing one should start with, I guess, is the partition function.
Yeah, so that's the thing that I want to study next. So I was not even actually expecting that there should be something like this that emerges. What's encouraging is that this structure here that you see, that the resulting answer looks very much like entanglement in.
But isn't it guaranteed that if you take the ADS problem and you insert the right I's, you'll go back to the, you take the DS problem and insert I's, you'll go back to the ADS problem?
Yeah, except that you get those I's that are left over. That's all.
So there was something significant about the I's you got here. I mean, if you.
Yeah, I'm wondering actually if the I's actually mean something. That's what and so at this level, at the level of these bulk calculations, I don't think one can settle it. So one really has to ask whether if I take the SPN theory or something of that kind and just set up, this is this theory of ghosts and so on. Just follow through that and see what you get. That's something I want to think about, but I really don't have. I mean, yeah. But it's just that this answer at the end of the day looks like it looks like entanglement in that. It was guaranteed from the point of view of the analytic continuation in some ways,
right.
Except that you were not guaranteed that the I's will all conspire in the right way.
Okay,
from the point of view of the dual, no, because you already see that's not happening in the other dimensions. For DS3, DS5, you don't get that. You get something else.
Okay.
So I don't know if it sort of looks accidental or at least miraculous or whatever that exactly in DS4-CFT3 where I have a little more confidence on DSCFT that in fact you get something like this.
Okay.
Yeah. So okay, so I'll close here. So here are a bunch of conclusions. We saw this Lightlike limit in some ways arising that's suggested by these string generalizations of these non-relativistic theories, where entanglement in the low dimensional theory arises on these null time slices. This whole structure that emerges here is reminiscent of ultra locality in light cone field theory. might be interesting to understand this better and systematize this better in the weak coupling like cone field theory. And here's this whole discussion of extremal surfaces that we've just seen, and I'm curious what that might mean. Thank you.
Questions? Well, I guess there were lots of questions during the talk. So let's thank Narayan again for a very interesting talk. So now there'll be coffee and we'll convene at 4 o'clock.